everyone. Today we are going to move on to our final unit on electrochemistry. This particular unit we're going to just introduce you to some of the basic important concepts that you are going to need for post-secondary next year. Overall, we're going to be looking at and studying what oxidation and reduction and how they are paired in chemical reactions, in which electrons are going to be transferred from one substance to another in a very predictable way. So this first section, we are going to learn and understand what the terms reduction and oxidation mean, and be able to determine the oxidation numbers of an atom in a compound or within an ion, and be able to manipulate and identify different reduction and oxidation reactions. So that's going to be the focus in today's lesson. So let us consider from grade 11 this simple single displacement reaction that we have studied before. All right, so we know that this is a single displacement reaction because it consists of a single element and a compound, an aqueous compound solution. So our metal is being placed into this solution. So this is a single displacement reaction. All right, RXN stands, my short form, for reaction. So we see here what we can do is write what we call the total ionic equation. And if you recall from grade 11, we did this as well. Anything that is in a solid, liquid, or gas state, we leave it as it is. It stays intact. However, anything that is aqueous and is ionic in nature, it is dissociated into its respective ions. So the copper 2 sulfate here, since it's aqueous, is going to ionize or dissociate into copper plus 2 ions and sulfate ions, SO4 negative 2. So you have to recall your nomenclature here in order to determine the charges, as well as using your periodic table to predict their charges by applying the crisscross rule in reverse. All right. Then if we go over to the product side, we see that copper is a solid, so we leave it as it is. And then we've got zinc nitrate, which dissociates into zinc ions with a charge of +2, and sulfate ions with a charge of -2. Reminders that sulfate is one of those ones that we expected you to memorize last year. Okay, now that's the total ionic equation. When we want to determine the net ionic equation, we canceled out any spectator ions. And if you recall from grade 11, the spectator ions are the ones that are found on the either side of the equation. So we see here that SO4 negative 2 is found on both the left and right side of the equation. Hence, these are my spectator ions, and they are not involved in the reaction, so therefore we can cancel them out. Now, whatever is remaining, in this instance here, there's only one spectator ion, and so therefore whatever is left over now becomes my net ionic equation. So I take everything else, and that's why it's important to include the states so we know what state they are in. And now we've got my net ionic equation. Now, what's going on in this particular reaction? Two very important things. First, there's an oxidation, which is defined by the loss of electrons. And then we also have a reduction taking place, which is the gain of electrons. And a good way to remember this is this little sentence or little acronym that says Leo the lion says grr. L stands for lose. Loss of electrons is oxidized, and gain of electrons is reduction. All right, so that's a good little way to remember that. Oxidation is the loss of electrons, reduction is the gain of electrons. And so in these types of reactions, you can't have one without the other. They need to occur. Both of them need to occur. So hence, it is known as an oxidation reduction reaction, or in short form, we call it a redox reaction. So what actually is taking place here? We see here that the zinc has gone from its elemental form. All right, so when it's in its elemental form, it's going to have a charge of 0. It's neutral. And over here on the product side, we see that zinc is now an ion with a charge of +2. Hence, it has lost 2 electrons. Okay, so it's lost 2 electrons. While we see that copper has gone from a charge, it's an ion, it has a charge of +2, and it's gone to become in its elemental form, which is neutral, and so therefore it has a charge of 0, we say. And so we see that it's gone from +2 to 0, which means it has gained. There is a gain of 2 electrons. So therefore the gain of 2 electrons, this is my reduction, and the loss of 2 electrons represents my oxidation. So hence you can't have one reaction without the other. Now, a reactant that oxidizes another reactant, we call it the oxidizing agent. So lots of new terminology here. And the reactant that reduces another reactant is called the reducing agent. So if we look at our example that we just did, okay, we see here that the zinc is my reducing agent because it's the one that's donating the electrons. Hence, it's undergoing oxidation. While my copper 2 ions is the reducing agent, which is accepting the electrons and undergoing reduction. All right, so it's very important in this first section that we understand and know all of our terminology. Now, we can see what's happening with the electrons using what we call half reactions. So to monitor the transfer of these electrons during a redox reaction, we can actually represent them as 2 separate reactions, the oxidation and reduction reaction. And the half reaction, these are always going to be balanced because they're always also going to show the number of electrons that are involved in either of these oxidation reduction reactions. So in these reactions, when we write them as half reactions, we always include the electrons that are involved, and we must always write them in pairs. So this is very, very imperative that they are written in pairs. And so if we look at the example that we just did up above, we could write the oxidation reaction as a half reaction. And what we see here is that the zinc metal is losing 2 electrons in order for it to become a zinc ion. And we include the electrons that are being lost on the product side to show that it is a loss of those electrons. Now the reduction portion, so we always have to write these as pairs. We need to include both reactions. We see that we've got copper ions and we're gaining 2 electrons this time. So therefore it is written as part of the reactants. And now we're going to form our product, which is copper solids. And if you'll notice here, if I add these 2 together, it will result in the net ionic equation. Okay, it will result in that because what we would do then is take away the electrons and add up what is left over between these 2 half reactions, and lo and behold, we get our original net ionic equation. All right, so this shows us that there is electrons being transferred from one element to another. Now, another important thing here is being able to keep track of our electrons within these redox reactions. We have to know how to assign oxidation numbers. All right, these oxidation numbers are also known as our oxidation states, and there are a certain set of rules that we need to follow in order to solve for them. They are summarized in this table. All right, so these are the rules that you need to know and remember. Some of them are pretty straightforward and they make sense, with some examples on in the column, second column here. So the first one is that any element in its elemental form, so it's not combined with any other element, is always going to be assigned an oxidation number of 0. Okay, so if we look at potassium, hydrogen, even though it's a diatomic molecule of H2, it's still going to be given an oxidation number of 0. P and phosphorus, all of these, regardless if it's a metal or a nonmetal, any element which is in its elemental form is going to be given 0. The oxidation number of a simple ion is going to be given the charge of the ion. So calcium has a charge of +2, so therefore its oxidation number is +2. The oxidation number of hydrogen in most compounds is always going to be +1. There is an exception, and that is when it is found as a metal hydride. So here's an example of a metal hydride. Okay, sodium hydride. In this instance, hydrogen does not have a charge of +1. It will be -1. All other cases, may it be found in water or in an acid or in ammonia, we always assign hydrogen as +1. Oxygen in most cases, another very important one to remember, is always +2. The exception obviously is with peroxides. All right, it's going to actually have a charge of -1. All right, it's going to have a charge of -1. Otherwise, it's always -2. Elements in group 1, you will always assign them a charge of +1, and all the elements found in group 2 will always have an oxidation number of +2. The sum of the oxidations numbers within a compound is always going to be equal to 0. Okay, so if we look here in water, there's two hydrogens, each with an oxidation number of +1. And there's an oxygen with an oxidation number of -2. So 2 times +1 plus -2 equals 0. All right, the sum should always be 0. Now the sum of the oxidation numbers for a polyatomic will always equal the charge of the ion. Okay, so if we look at hydroxide, oxygen is -1, hydrogen is +1. If I add -1 plus 1, it gives me -1, which is the charge of my polyatomic ion. All right, so now let's do some examples in how we can assign oxidation numbers to the various elements. Okay, so if we take a look here, we see that beryllium is going to have an oxidation number of -1. Okay, because that is the charge if you look on your periodic table of group 1. So bromine, is going to have a charge of -1. Now what we're going to do is we're going to let X represent the oxidation number of silicon. Okay, we're going to let X represent it. And so therefore we've got X plus, there's 4 bromines, each at -1, is going to equal 0. The reason for that is because this is a compound, all right? So it's going to be 0. So if I solve for X, it's going to give me an answer of +4. All right, so therefore silicon has a charge of +4 and bromine is a charge of -1. Now you don't have to do all this work. Obviously some of these are going to be very easy to do. You can just do them in your head. All right, let's do the next one. So based on the elements that are in this particular compound, we see that we know hydrogen always has to be +1. And usually what I do is I always put a circle around the oxidation number so I don't mix it up with any charges that may be present in the polyatomic ions. So it has a charge of +1. Oxygen we know has to be -2, so the one that I'm looking for is actually going to be the chlorine. All right, so we're going to let X represent the oxidation number, which is equal to chlorine. All right, so that's what we're going to do. So solving this like a mathematical equation, I know I've got one hydrogen with a charge of +1. I've got X, which is going to represent the oxidation number of chlorine. And then I have 4 oxygens with each having an oxidation number of -2. This is all going to equal 0 because I know this is a compound and the sum of the oxidation numbers must equal 0. So now I'm going to solve for X. Okay, and so -8 +1 is -7, and when I bring it over to the right side, the oxidation number for chlorine here is going to be +7. All right, so that gives me the oxidation number there. All right, looking at my last one here, we've got the dichromate ion. We know oxygen is -2. We're not sure of the chromium, so let's solve for it. Once again, I'm going to let X represent the oxidation number for chromium. Okay, and we're going to set up our equation, but this time I have 2 chromium, so I'm going to say 2X plus there are 7 oxygens, each with a charge of -2, and because we've got a polyatomic, this time it equals -2. Once again, I got to solve for X. Okay, and so now I've got my 2X equals, I got -14, 7 times -2 is -14. When I bring it to the other side is +14, -2 gives me +12, and now X equals +6. So the oxidation number for chromium in this particular compound is +6. Okay, so that's how we assign oxidation numbers. All right, so for your homework today, you are to read over section 9.1 and please try these homework questions in the textbook. Good luck, and we'll see you in the next lesson.